You know all that energy your car uses to get going? Well, what happens when you slow down? Usually it's just wasted as heat. But what if it wasn't? What if you could capture it and put it back to work? That's the whole idea behind regenerative braking. And today, we're going to dive into how this tech is changing everything from our daily commute to trains and even how we get back from space. So, how does this incredible energy recycling actually work? Let's find out. I mean, it almost sounds like magic, doesn't it? The idea that braking could actually charge your car. Think about it. Every single time you hit the brakes, or even just take your foot off the gas in stop-and-go traffic, you could be sending a little bit of juice right back into your battery. And this isn't some far-off sci-fi concept. This is the very heart of regenerative braking. And it's happening right now in millions of EVs all over the world. Okay, so how on earth does a car capture energy just by, slowing down? Well, it all comes down to some really clever engineering that completely flips the role of the electric motor on its head. Let's break down the mechanics behind this so-called magic. So here's the official definition, but really at its core, it's super simple. Kinetic energy is just the energy of motion. In a normal gas-powered car, when you step on the brake pedal, all that forward momentum gets turned into heat by your brake pads, and it's just gone, wasted. A regenerative system looks at that and says, whoa, hold on a second. Let's not just throw that energy away. Let's recycle it. And this is how it happens, broken down into 4 simple steps. So, step 1, your electric motor is doing its normal job, using power from the battery to make the wheels go round. But then, step 2, the second you hit the brakes, that motor completely reverses its function. It becomes a generator. See, the car's own momentum is still turning the wheels, right? So now, in step 3, the wheels are turning the motor, and that leads to step 4. That mechanical spinning energy gets converted back into electricity and sent straight back to the battery. It's brilliant. This diagram shows the whole thing in action perfectly. You can see the electric motor. This one is a super efficient brushless DC motor hooked up to the front wheels. When you hit the accelerator, power flows from the battery to the motor. Simple enough. But when you brake, everything reverses. The wheels start turning the motor, and that captured energy flows right back to the battery. It's a beautiful, elegant, two-way street for energy. Now, this all sounds amazing, right? And it is. But this whole idea of getting energy back every time you slow down, well, it leads a lot of people to a question that seems pretty logical, but it's a question that brings us to the biggest myth about this technology. So let's just tackle it head on. The question is this: does this create infinite energy? I mean, if you get energy back every time you brake, could a car just power itself forever? Could you literally drive across the country without ever plugging in, just by braking enough? It's a pretty tempting thought, you have to admit. The answer? A simple, definitive, and scientifically crucial no. As much as we would all love a perpetual motion machine, the laws of physics kind of have a say in the matter. So if it's not giving you infinite energy, how good is it really? Well, the most advanced systems out there today can recapture about 60 to 70% of that braking energy, which is honestly pretty amazing. But it's not 100%. So the big question is, why not? Where does that other 30 to 40% of the energy go? Well, it's because of a fundamental rule of the universe. Every time energy changes from one form to another, you lose a little bit. It's like a tax you can't avoid. In a car, that energy is lost as waste heat coming off the motor and the battery. It's lost to good old-fashioned friction in the mechanical parts. It's even lost to the electrical resistance in the wires. The bottom line is, you can never get more energy back than you used to get the car moving in the first place. And this is where the engineering gets really tricky. This quote just nails the central challenge. On one hand, you want to save every last drop of energy you can, but on the other hand, your number one priority has to be stopping the car safely and reliably. And as it turns out, those two goals, they're often in a fight with each other. So that brings us to the brains of the whole operation. How do engineers build a system that can walk that tightrope between maximum efficiency and absolute safety? Well, it's all about creating smart braking strategies that can figure out the best way to stop the car in any given situation. Let's take a look at 2 common approaches here. First, you've got what's called an eco strategy. This one goes all in on saving energy. When you're braking lightly, it only uses the electric motor, so you get the most energy back. The downside? On a slippery, low-friction road, that might not be the most stable way to stop. Then you have the serial strategy. This one is all about safety first. It always blends the regenerative braking from the motor with the car's traditional mechanical brakes. You get a little less energy back, but you get rock-solid, predictable control no matter what. Okay, This graph might look a little complicated, but what it's really showing is the strict rulebook that engineers have to play by. That red line, for example, is a safety regulation from the ECE. The system has to be designed to make sure the braking force is distributed properly between the front and rear wheels to prevent them from locking up. So the whole game for engineers is to get as much energy recovery as possible without ever crossing that red line, because that's when you risk losing control. All right, so we've seen how this smart braking works in our cars, but this core idea is so powerful that it's being used in some much, much bigger machines. So now we're going to go from the highway to the railway and even further. Just try to imagine the incredible amount of kinetic energy a high-speed train has when it's at full tilt. When one of these things slows down, all that energy doesn't just get wasted as heat. As this chart shows, the system captures it, stores it, and can even feed the extra electricity right back into the smart grid for another train somewhere else on the line to use. We're talking about recycling on a massive, network-wide scale. And this is where the same basic principle takes a giant leap into the future. Seriously, check this out. For spacecraft, there's something called an electrodynamic tether. It's basically a long wire that uses a planet's own magnetic field to create drag and slow the spacecraft down with zero fuel. And then there's ballistic reentry. For vehicles coming back into the atmosphere at insane hypersonic speeds, magnetohydrodynamic, or MHD braking, uses powerful magnetic fields to interact with the plasma that forms around the vehicle, creating this incredible, controllable braking force. So what's the secret sauce that makes all of this complex stuff actually work? You guessed it, AI. As you can see here, artificial intelligence is the master controller, the brain of the operation. On a train, it's constantly tweaking the brake pressure to get every bit of efficiency. For reentry vehicle, it's making instantaneous adjustments to that plasma field to guarantee a safe landing. AI is what makes these amazing systems not just possible, but also unbelievably efficient. So think about where we've been. We started with a pretty simple idea in your car. Let's not waste the energy of motion. And we took that all the way to landing spacecraft from orbit. It really makes you look at the world a bit differently, doesn't it? Every single thing that moves has energy. So the final question is, from city streets to deep space, what will we recapture next?